Hey everyone, today we're going to talk about molecules and compounds. Make sure you have your periodic table for this, okay? So, just remember from chapter 3 that compounds are different than elements. So like an element from this example would be graphite, but sucrose is our compound. And although carbon is in that sucrose, they are very different things. They have different properties, things like that. Okay, same thing with sodium and chlorine, but when we put them together and make salt, they have completely different properties. So just remember that elements and compounds, even the elements that make them up, have different properties in their compounds. Okay, also recall that compounds have fixed, definite proportions, but a mixture has whatever proportions they want. Also, most substances that we're going to encounter in our everyday life are really going to be compounds and not elements. Okay, also recall, again, mixtures, proportions don't matter, but for compounds, they are absolute, they do matter. As far as this law will not be, the math part of it won't be tested, but it could appear on your homework. The definition of the law could be tested, so you do need to go ahead and write that down. The law of constant composition tells us that all samples of a given compound have the same proportions as the elements that make them up. So they're the same proportions always for specific compounds. So just here are some examples I'm going to go through. Okay, so here, water is an 8-to-1 ratio of oxygen to water based on their mass. Nitrogen or ammonia is a 4.7-to-1 ratio of their mass. But remember that these atoms combine in whole number ratios. We never see subscripts as decimals or fractions. They're always going to be whole numbers. So here's an example. Again, the only place this may appear is on your homework. Okay, it's not hard, so we're just comparing. It wants to know, are these two samples the same compound? Okay, so to verify that, we're going to do a mass ratio. So 17.1 grams of oxygen to 6.4 grams of carbon. Okay, they both happen to come out to 2.76 oxygen to every 1 carbon. Sorry, 2.67 to 1 carbon. Okay, so yes, these are the same compound because their constant composition is the same. Okay, there is another example. I'm not going to work it. Also, it doesn't even matter if you flip them as long as the same element stays on top. You can check to make sure that they're the same. Okay, so formulas, they're going to tell us the elements present and how many of that element is going to be there. So like for water, we have 2 H's and 1 oxygen. Also remember, a subscript of 1 will not be shown or is omitted. We don't normally write that. So don't write that in Mastering Chemistry. Make sure you do not write it. Okay, here's again, it's got the symbol from the periodic table along with subscripts if there is more than 1. As far as subscripts go, again, they need to be whole numbers. Okay, and they tell us the relative number of each atom in that compound, or each type of atom, so each element. So like if we're looking at this sucrose, there are 12 carbons, 22 hydrogens, and 11 oxygens. But if we're looking at sodium chloride, it's just 1 sodium and 1 chlorine because it's a 1-to-1 ratio. There are no subscripts shown. This slide is wanting you to know you cannot change the subscripts just because you want to, okay? A subscript is there for a reason, and when you change a subscript, it changes the compound completely. It also changes the properties of that compound. So like carbon monoxide is something that comes out of our car exhaust. It's a deadly gas. It also sometimes can come from your gas stove or your gas furnace that has adverse effects on humans, and eventually it'll kill you if you have too much exposure. So if you have a gas stove or a gas furnace, hopefully you have carbon monoxide detectors at home. We have those. They plug into the wall. But carbon dioxide, so that's CO2, it's something that we breathe out, and it's not harmful to us. Like, we're surrounded by it all the time. So a chemical formula will list the metallic elements first. So metals will always come first. If they're both nonmetals, the ones to the left on the periodic table and toward the bottom, those are more likely to act metallic because they're closer to those metals. So those are going to be the ones that come first. And here is a list if you want to write them down, but you shouldn't need it. You should be able to tell, hey, yeah, this is closer to the metals than the nonmetals. All right. So as far as this slide goes in these examples, they want you to write the elements formulas or as compounds. And remember, the most metallic comes first. So A is going to be 2 aluminums to 3 oxygens because aluminum is a metal. B, we've got sulfur and oxygen. It's going to be sulfur first because it's farther down on the periodic table. Okay, and then for C, carbon comes first because carbon is next to a metalloid. I do want to make you aware, if carbon is present, it's only nonmetals, carbon definitely needs to go first. We are carbon-based life forms. Everything that we know about life is based around carbon. So carbon needs to be the element that's first. Okay, let's do a few more. Silver and sulfur. So silver is a metal, a true metal. Okay, nitrogen and oxygen. So those are both nonmetals. Nitrogen is farther to the left, so it's going to be N2O. For C, we've got titanium and oxygen. Again, titanium is a true metal while oxygen is a nonmetal, so titanium will come first. If you have questions on these, please let me know. Oh, okay. Now we're going to talk about polyatomic ions. So just remember, poly means more than one. Hopefully you remember talking about polygons in math, specifically geometry. So it's got more than one atom, and it's an ion, which means it's got a charge. Okay, these polyatomic ions, they act as a whole group or a unit. Okay, there will be subscripts that are attached to the polyatomic, and you will need to make sure they stay there. They're not going to move any ever. Okay, if you have more than one polyatomic, then you need to put it in parentheses if there's a subscript. Okay, and that subscript is going to be more than one of them. You'll see. So here, I've got one magnesium, but I've got 2 NO3s because it's in parentheses. So just make sure to distribute whatever's outside of the parentheses back in, just like you would in math. So that means I have 2 nitrogens and 6 oxygens because you've got to do your distribution. All right, so here's an example. Magnesium, phosphorus, and oxygen. I see 3 magnesiums. It is not in the parentheses. We do not distribute anything to that. We've got 2 phosphorus atoms and 8 oxygens because of the 2 times 4. For potassium, I've got 2 of them. Sulfur, 1. And oxygen 4, because there's no parentheses there, so there's no distribution. This last one, I've got 2 aluminums, 3 sulfurs, and 12 oxygens. Okay, if you need help with that, let me know, but this really isn't bad. Okay, the empirical formula is going to give us the relative number. And when it says relative number, this means smallest whole number ratio. Okay, so this is going to be the most reduced of the subscripts. A molecular formula is going to give us the actual number of atoms. So in reality, they're given H2O2 example, but I think glucose is better. Okay, so glucose is C6H12O6. That is a molecular formula because that's how we find glucose in nature. If I want the empirical formula, so I'm going to put MF, I need to reduce those numbers, and hopefully you can see I can reduce them by 6 to CH2O. Okay, that will always be some whole number multiple. The molecular formula will be a whole number multiple of the empirical formula. And the molecular formula can be the same as the empirical formula, like for water. Okay, I can't reduce that anymore. It's already as low as it goes. Okay, this is just showing you, we're about to see some different models. It does give you the different colors. If you have a homework question or a test question, they'll tell you what the colors are, and so you don't need to write these down. Really though, we're going to focus on the ball and stick and space filling model. I know y'all have seen these. This is what the book likes specifically. But for this chapter, it's going to want you to count and tell them how many of each atom there are. So here there are 4 hydrogens, you can see that, and 1 carbon. Okay, and again, they would tell you what color is what. So here are just some more of those space filling models for water. All right, recall from chapter 3 that pure substances can either be those elements or compounds. Now, elements can either be broken into atomic or molecular, and then compounds can also be broken into molecular or ionic. There are slides for all of this. So atomic ones are just single atoms. They're found that way all alone. Molecular ones are not found alone. They're found in either 2s or multiples. Most often they're found in 2s. Compounds could either be molecular or ionic, which we're going to discuss. So remember those atomic elements, those are single atoms. And most elements are these atomic elements. Okay, molecular elements are more than one. And they're going to be mostly diatomic molecules, which means there's 2 atoms that are bonded together. And this is how those are found in nature. So diatomic, 2 atoms. Okay, you do need to know the diatomic molecules, which are on the next slide. But here we can see mercury, they're all little individual mercury atoms. But on the diatomic one, like chlorine, they're bonded together. They've got this little mark here. So that's saying they're squished together, they're bonded together. Unlike those mercury atoms, which are individual atoms. Okay, here are the diatomic molecules. You do need to write them down. Okay, so if you look, they do form a 7 on the periodic table plus hydrogen. I normally call these the gens. That's because the first 3 end in gen, and then the last 4 are halogens. Okay, make sure you mark these, but for me, I'd mark them on the periodic table. Y'all people at home, if you do not have a printed periodic table, it will really benefit you to get one. Okay, whether your parents have to print it somewhere else or you've got to go somewhere and have it printed, you got to do something. Okay, molecular compounds. Those are compounds that are formed by 2 or more nonmetals. Ionic compounds are a metal and a nonmetal in most cases. Metal and a nonmetal. Okay, they can be cations and anions, which we will talk about in a little bit. That really comes with our polyatomics. So, if a metal comes first and it's a compound, it's ionic. If it does not, it's molecular. Also, the smallest units of molecular compounds are molecules, which is what you're used to for compounds. But ionic compounds' smallest unit are called formula units. And that's because if you look, most ionic compounds are crystals. And you have to pull out a little tiny piece because they're all really shoved together. So ionic compounds, again, smallest unit is a formula unit. I do need you to know that electrons are transferred from the metal to the nonmetal, and this is what creates those ions, which is why they're called ionic compounds, because they have ions. So, Here we're just classifying, are we an atomic element, which I'm going to abbreviate as AE, molecular element, remember these are diatomic, molecular compound, or ionic compound. Okay, so krypton. That is just a normal atomic element. It is not one of the gens. B, that is very clearly a compound. So then you need to see, is that a metal, cobalt, or is it a nonmetal? So hopefully after some time you'll see that cobalt is a metal, so it's an ionic compound. C, nitrogen. That is one of those diatomic ones, and the giveaway is it ends in gen. So this is a molecular element. Sulfur and oxygen are both nonmetals, so that's a metallic compound. And then potassium, this is obviously a compound. Potassium is an alkali metal, which makes it ionic. Okay, you will have to be able to sort these on the homework and on a quiz or a test. So chlorine, that is a halogen molecular element. NO, that is a molecular compound. Both of those are nonmetals. Gold is an atomic element. Sodium oxide, that is an ionic compound because sodium is an alkali metal. Chromium is a transition metal, which makes that an ionic compound. As always, if y'all have questions, please let me know. Now we're going to start writing formulas. Okay, the goal of ionic formulas is that the sum is 0. So the sum is 0. It does get to that later, that there's equal positive and equal negative charge, which means the total sum is 0 for ionic compounds. This means when we write them, we're going to have to do some special finagling to make them that way. So when we write the symbol, the metal and its charge, and then we write the nonmetal and its charge. Then we crisscross, that's what this one is, crisscross the magnitude, which is like the absolute value. So we're only pulling down the number, not the plus or the minus. Then we reduce if possible, but that's only if we can. So here we can see they write the metal and the nonmetal with their charge. They bring down the numbers and only the numbers. When this happens, the plus and minus disappear. And there's our formula. The reason we do this is because we know aluminum is 3 plus. I have 2 of them, that's 6. Now I've got 3, 2 minus, that's negative 6. So if I add those together, I'm going to get 0. Because the sum of ionic compounds must be neutral. Again, when you write the compound, there is no plus or minus. Those go away when you bring down the numbers. Here are some common polyatomics. I did post a polyatomic chart on Google Classroom. Make sure you look at that. So we're going to do aluminum and oxygen, which they did already do. We cross the numbers, and I get Al2O3. Let's do one they haven't done. Strontium. Strontium has a +2 charge. Chlorine has a minus charge. That does mean -1, just like in math. We do not write ones unless they're absolutely necessary. Okay, so we're going to bring down our charges. So I've got 1 Sr and 2 Cls. Magnesium and oxygen. So they do get Mg2O2, but remember that reduce if possible. So if they're the same, they just become 1s at the bottom because the numbers are going to disappear. It's like 2 divided by 2 is still 1. It's the same thing here. Now one more, aluminum and nitrogen. I've got Al3 plus and 3 minus. We cross them, and I get rid of my 3, so it's just Aln. That's the reducing if necessary part, or if you can. All right, now we're doing it with nitrate. So nitrate is NO3 minus, again, on your polyatomic chart, and calcium is Ca2 plus. So we still crisscross. Now, some people here think that 3 moves. That 3 is attached to the nitrogen, not the nitrogen, the nitrate on the oxygen. So I've got Ca and I've got NO3. The 2 comes down outside of the NO3. So because we've got that polyatomic present and a number came down, it needs to be in parentheses. But that's only if a number comes down. So on this next example, I've got aluminum and phosphate. Okay, we crisscross, but notice they're both 3s. So this means it's just AlPO4. That 4 stays because it belongs to the oxygen in phosphate. But there's no numbers that came down because they canceled out. So we don't need parentheses. One more, sodium and sulfite. Okay, we bring them down. So this one is Na2SO3. Again, there's no number that comes down for sulfite, so it does not have to be in parentheses. As far as naming compounds goes, we're only naming ionic today. Again, make sure you have your periodic table because you're going to need to be able to spell these. Remember, ionic is a metal and a nonmetal. That's what makes an ionic compound. We have 2 types of metals in ionic compounds. We have the ones that form one type of ion. These are the ones with A's at the top. And they have charges. We wrote them at the top of your periodic table. These are mostly transition metals that have more than one. Okay, there are a few exceptions, but the transition metals have more than one ion. The metals that form just one ion are going to be type 1. So this is type 1, and this will be type 2. They do have different ways to name, so it's very important you're able to identify what's what. So type 1, again, those are the ones with charges that we wrote at the top. They have A's on top of their columns. Type 2 are generally transition metals. Those are the ones with B's. Plus some. So also for up here, it's PB, SN, SB, BI, and TL. So there's 5 of them that you need to add. They're not transition metals in reality, but they behave that way with their charges. Okay, so these are our 5 that behave like transition metals, although they do not belong to the transition metal section. Okay, if you do not have these written, please do so. Okay, also for zinc, I want you to write its charge in the box, physically in the box. Same thing with silver. Don't do scandium though. We don't normally see scandium in compounds. But zinc and silver are pretty common. So make sure you know zinc is always going to be +2. It's going to act like a normal metal, not a transition metal. Same thing with silver. Okay, but these ones, these are type 2. Even though they're not in the type 2 section of the transition metals. Okay, you don't have to write anything on this slide, but the reason transition metals don't have charges written above them is because they have different charges. So like chromium can be 2 or 3, but copper could be 1 or 2. And the way we're going to name those is Roman numerals, which we'll get to in a minute. So first, let's talk about how to name type 1. So these are type 1. We're going to write the metal. We're going to write the nonmetal, but instead of having the suffix "-ine" or "-gen" or "-ide", we're going to change it to "-ide". At the end, we're going to take off the suffix and add on "-ide". So here we can see that we've got Na is sodium, and Cl is chlorine, but it goes to chloride. Okay, and here are some common anions if you need to write them down. So, I've got magnesium, and F is fluorine, but it becomes fluoride. It is very important that you spell this specific element correctly. It bothers me when you spell it wrong, and I will count it wrong. Your periodic table has names, Do not do something that doesn't, like, don't make up elements. That's not what we're doing. Just spell it the way it says on the periodic table. Okay, let's do another one. Potassium. And then Br is bromine, so it goes to bromide. One more, that's zinc. Remember, that's a transition metal, but it behaves like a one-charge metal. And nitrogen goes to nitride. Okay, you are going to need to practice. You are going to need to know what type of metal is what before you start doing this naming. We will have a quiz on this on Tuesday. Okay, as far as type 2 goes, these do not have set charges. This is type 2. So we're going to put the Roman numeral in parentheses. That's the charge. That's how we're going to be able to tell what charge it is. So here we can see with copper, we've got copper 1 and copper 2. If you do not know your Roman numerals, you should write them down. You need to be able to count to 7 with your Roman numerals, because that's as high as they can go. So, if you don't know them, write them down, especially 4. Okay, sometimes 4 is the one I see that's off. So, again, this is type 2. We name the metal. We write the charge as Roman numerals. We write the nonmetal with IDE. Okay, in order to find the charge from a formula, you have to remember where those charges came from. So remember, this number down here belonged to iron. That was its charge because we crisscrossed them down. So in this scenario, that is iron 3 chloride because that 3 came from iron. Okay, so this 4 came from lead. So this is lead 4 chloride. Okay, this one is kind of tricky. A lot of students say this is lead 1 oxide, but you need to be careful with oxygen and sulfur specifically. We know that oxygen has a 2- charge, which means if this truly was 1, it would be Pb2O. But in reality, this is 2, so they cancel. So this is lead 2 oxide. So, if you have an oxygen or a sulfur next to a metal, you need to check if there's a number here, in this spot after the metal. If there is no number, multiply what you think the charge is by 2 because that means it was reduced. Only if there's no number there. These are the most common mistakes for naming these. Okay, now we're going to talk about naming with polyatomic ions. It is the same process. You need to identify, is it a type 1 metal? Is it a type 2 metal? Then, the polyatomics keep their name. They do not change at all. So, here I've got type 1. Name the metal, potassium. Nitrate is my polyatomic. Okay, here, OH is my polyatomic. So this is type 2. So I've got iron 2 hydroxide. Again, this 2 came from the other side of iron. Occasionally, you will have 2 polyatomics together. That means ammonium comes first because it's the only one that's positive. So that's NH4+. And then we've got nitrate or whatever else is attached to it. Make sure you understand the charges that are shown for polyatomics, those are what's crisscrossed down. So if you don't see one, it's not that it's not that polyatomic, it is. It just either canceled out or it's shown in another way as a subscript. Okay. Most polyatomics are going to be oxyanions. This means they have a negative charge and oxygen is present. So, the set name ends with ATE. And if you look at your polyatomic chart, most of them are ATEs. However, when they lose an oxygen, so 1 fewer oxygen, is ITE. So ATE is not a set number. Neither is ITE, but the ite is one less than the 8. And look, the charges stay the same. The only thing that's changing is how many oxygens there are from 8 to ite. As far as the prefixes go on polyatomics, hypo means less than, and per is going to mean more than. So hypochlorite has one less oxygen than chlorite. Perchlorate has one more oxygen than chlorate. Okay. Also on your homework, it does tell you you're going to need to put the word ion if it just asks for a polyatomic. Also, while we're talking about your homework, and I want to talk about your test. Lots of you, your problem on your test were you didn't have enough time. Like you ran out of time, and they're all going to be timed. I think the biggest problem was that y'all were flipping through your notes, and instead of studying, which is what you should have done, you just decided, oh, it's open note. But yes, it's open note, but you're wasting time looking through your notes. So, I do suggest you have this sheet. I would maybe highlight the most useful ones, things like that from the polyatomics. Okay, so now we're going to practice naming them. This is a type 1 because potassium is it's an alkali metal. So this is potassium. Then we go look on our chart for CrO4. I see it. It is chromate. So we just name it potassium chromate. Manganese is type 2. That's a transition metal. Okay, we'll wait for the Roman numeral. That is nitrate. Okay, and then this one's easy because it's got that 2 down there. So this is manganese 2 nitrate. Okay, this slide is just telling you, hey, by the way, polyatomics are in all sorts of everyday household chemicals. And not just chemicals, but food and medicine, things like that. So sodium hypochlorite, that is bleach. Okay, sodium bicarbonate, that's just baking soda. Calcium carbonate is Alka-Seltzer and Tums. And then the sodium nitrite is a food additive that we add to packaged meats to keep it from growing bacteria. Also, hot dogs fall into that. Okay, so if y'all have any questions, please, please, please reach out. Y'all